Okay, so thank you everybody for joining us today. Today we are very pleased to have Jonathan Libgober from USC, who's going to talk about implementing evidence and acquisition, time dependence in contracts for advice. It's a joint work with Yingkai, and we have as guest panelists Alex Bloedel and Yingni. So thank you all for joining us, and thank you for your attention. So just as a reminder, next week is Thanksgiving, and so we're not going to hold any seminar, but we'll be back after this 1 week gap, and we're going to have Hesky Bar Isaac from Toronto, and he's going to present the paper under the name of Selling Attention Through Steering and Certification. So thank you, Jonathan. The screen is yours.
Thanks so much. I should give one disclaimer before I start, which is that I was actually quite sick for the past 2 weeks. I'm okay, but if I start coughing a lot, don't be alarmed. I'm fine. As was said, this is joint with Yingkai, who is in the chat and able to answer questions. And this project is part of an agenda interested in studying contract design for the purpose of information acquisition. So I'm going to be writing down what I think is a reasonably general theoretical model. It's going to have an expert who is going to be able to learn about the state, but is not going to have any intrinsic interest in doing so. We're going to be, the way they would learn about the state is using a particular process we'll write down, which we call searching for evidence. It is what it sounds like. Undertaking this information acquisition involves cost. Okay, so given that they have no inherent interest in learning about the state, and given the information acquisition is costly, we're going to need to have incentives provided in order for them to undertake this activity. So we're going to be having a designer, and this designer's interest is going to be to get the expert to learn as much about the state as possible. Okay. Now, the designer is not going to be able to observe the effort of the expert, so this is going to feature moral hazard. Okay. Not only that, but we're going to be interested in cases where this evidence that the expert is searching for requires expertise both to recognize and interpret. So that means that the designer is not going to be able to understand what the meaning of this evidence, and so incentives are also going to need to be provided in order for them to report this truthfully. Okay. Now, given the combination of moral hazard and adverse selection, and given that this expert doesn't have any intrinsic interest in learning about the state, we have to have some kind of design. Something has to be designed in order for them to undertake this activity. We're going to be interested in cases where what the designer can do is specify rewards provided to the expert as a function of the underlying state. Okay, so we're going to assume that these rewards belong to some fixed bounds. And the reason this is going to be helpful is that because if the designer is providing rewards that can depend on actions of the expert as well as the state, then that incentivizes the expert to learn about the state, and it kind of endogenously makes them interested in acquiring this evidence. Okay, and so essentially you can think of our goal as being to design the decision problem that the expert will face in order to induce them to acquire information. Now, I think this, sounds like a kind of a lot of problems you might be interested in. And so there's lots of questions that you might want to ask and have been asked. Our starting point for our exercise is the observation that this idea that the expert, acquires information in particular via this, searching for evidence procedure, evokes dynamics very fundamentally. It's sort of, the idea that the process that's being engaged is something that doesn't happen in some one-shot setting, but is actually something that that unravels over time. And so given that the information acquisition process that the expert is facing is kind of most naturally modeled in this dynamic way, a natural question is whether the contracts should correspondingly be dynamic. Now, what do we mean by a dynamic contract? What does that mean versus a static contract? To be a little bit more precise, our question is going to be whether allowing for multiple elicitations can induce the expert to acquire more information. And that's going to be our main question. Just to give it away a little bit, the answer is going to be sometimes yes and sometimes no. So we're going to have a non-trivial answer to this. And by the end of the talk, I hope to give a lot of intuition about precisely when it's yes and precisely when it's no, not just saying sometimes yes and sometimes no. Of course, we're also interested in what are these optimal contracts anyways. I mean, our main question is going to be about do multiple elicitations help or not? But along the way, we'll kind of get some intuition for how the presence of dynamics influences the effort maximizing contracts, even in cases where they're static, and also some certain properties that characterize effort maximizing dynamic contracts in general. Okay, but I'll talk a little bit less about that today. Today, and really the paper's main message is about when is it the case that leveraging the dynamics can help. Okay. So I've kind of said a little bit about the model. I want to be a little bit more formal about what exactly the expert is doing. What is the design problem? I'm then going to I'm going to write down a static problem from this dynamic problem, which is going to be very helpful in terms of developing some intuition for why you might think that contracts should involve some dynamic elicitation. That's sort of the goal of walking through these static problems that we're going to talk about. And also because we sort of a little bit more straightforward to solve those problems. Okay, and then I'll turn to our main results on when static elicitation suffices. Okay, so here's the model. So we're going to have a binary state. It's going to be in 0 and 1. And it's going to be drawn according to a common prior, which we're going to denote D. Time is going to be discrete, going from 0 until capital T. So we think of T as the last date at which the agent can as the expert can undertake actions. By the way, I'll use the term expert and agent kind of interchangeably. I hope that's not confusing. We allow the length of the period to be indexed by delta. That doesn't really play much of a role in our formal results, but it's helpful to kind of illustrate solutions sometimes because we can draw nice pictures in this limit, and also it's helpful because as we'll discuss, there's a large literature on learning according to Poisson information arrival, and that literature is often cast in continuous time, and so it's sort of helpful for that. But we don't really need that limit to go to 0. Our results will hold for an arbitrary interval length. So this state is going to be initially unknown. And we think about this state as being publicly revealed at some point after time t. Okay? And so in particular that we're going to be able to write contracts on that realization. Our results, the ability to write contracts dependent on the state, sometimes that sort of seems a bit strong. Our results would hold just as well if instead of the state, what was observed was some binary signal that was correlated with the state. I'm not going to talk about that because it's just some added notation, but in some applications that perhaps that might be more natural to think about that you maybe don't see the state, but you see this signal. Okay.
So, Jonathan, can I
Yes.
ask one question?
Yes.
So, do you need an assumption that at the end of T, right, you observe this signal. This is how you are going to pay the agent for his report, right?
Yeah, so in the model we write down, we're going to assume that you'll be able to pay the agent as a function of the state.
Okay, do you need any assumption on this binary signal?
I don't think there's any.
So as long as it's informative.
Yeah, as long as it's informative, I believe.
Okay.
Yingkai can maybe correct me if I'm wrong about that, but I think, yeah, the key point is just that it's binary.
Okay.
But I'm not going to talk about that for the talk. Okay. Very good. So between 0 and capital T, the agent is going to be deciding whether they want to exert effort or not, and this is going to be a binary decision in every period. So if the agent exerts effort, that's going to cost something. That's going to be, it's going to cost C delta, okay, which is greater than 0. But what the agent gets is a possibility of observing what we call an informative signal, which we think of as evidence arriving, okay? So this signal S is going to be found with a probability that depends on the underlying state. So signals, we allow for two kinds of evidence that could be that could arrive. One we call a good signal, and the other we call the bad signal. I don't necessarily want to think about these signals as having normative value, but we like to use the terminology good and bad in part to kind of distinguish states and signals. So states are 0, 1, and signals are good and bad. Okay? And the idea is that the good signal is more likely to arrive in state 1, and the bad signal is going to arrive in state 0. Okay? So it could be that when the agent exerts effort, one of these this evidence or these informative signals arrive. Otherwise, with complementary probability, a null signal will arrive. Now, a null signal could itself be informative, right? The failure to find the evidence could itself provide some information, but we'll see that I want to have this distinction between these S signals and the null signal. Okay, so good evidence arrives. It could be good or bad. If evidence doesn't arrive, a null signal is observed. The agent also has the option of not exerting effort. In that case, they don't have to pay any cost. But if they, as a result, if they don't pay the cost, they get a null signal for sure. Okay. So far, I haven't said anything that really distinguishes state 0 and state 1. I'm going to make one assumption that does kind of give some more meaning to state 0 versus state 1, which is that if the beliefs drift over time, then they drift towards state 0, okay? So that's sort of reflected in this inequality. Now, it's possible the beliefs don't drift over time, in which case if you don't find evidence, you don't learn, your beliefs don't move. That's actually kind of the easy case, it turns out. And so, the case where equality isn't, we'll talk about it, but it's not so interesting. Most of the interesting cases are when the beliefs drift in the absence of evidence. And so the assumption is that in that case, they drift towards 0. Now, we do make one restrictive assumption within this class, which is that only one piece of evidence can be found, okay? So formally, so the null signal can arrive any number of times, but our assumption is that if you observe a non-null signal, so if you see this good news or bad news, then that kind of ends the learning process for the agent, okay? So once you see the signal, nothing else can be observed. So I want to talk a little bit, that is our big assumption, and I want to talk a little bit about it, what we think it reflects, why we think it's reasonable. The first thing I want to point out is that there's a very large literature about learning, using this Poisson technology, in particular, perfect Poisson learning, that in the limit as delta goes to 0, if you were to only have one signal, then that's sort of a special case of this learning process I wrote down, okay? So if you are in a setting where, only good news signals arrive, okay, then and they only arrive in the good state, in state 1, then that would be this kind of perfect, that would coincide exactly with this perfect Poisson assumption from, say, Keller-Rady-Cripps. So from that perspective, the novelty that we have in our learning technology is that evidence can either incriminate or exonerate a state. So it could be that you find evidence for state 0, or it could be that you find evidence for state 1. And it also can be inconclusive. So it doesn't necessarily need to reveal the state. And I want to emphasize those two properties because both of those properties are going to be very important for this kind of main characterization result that we have coming down the line. So this is very tracked. It turns out that, having one signal realization, one kind of realization of non-null evidence, it turns out to be very tractable. We'll sort of see that in kind of the next slide. But in terms of what kind of situation we think it reflects, I watched a lot of videos about, airline and, just planes and stuff like that. And so a lot of so one kind of example that I like is to think about, this expert as being someone who's investigating an airline incident, say on behalf of some government. Right. So if you think about a plane crashes or something happens to it, and you want to figure out whether this plane is safe to fly as a result. It could be that this is that this is a result of some pilot error that doesn't really say anything about the model itself, that doesn't reflect the design flaw, or it could in fact reflect a design flaw, in which case something needs to be fixed. Okay, and so in that case, the evidence that you find, it doesn't necessarily it could suggest pilot error, or it could suggest, a design flaw. So this state, evidence could be in either direction. It doesn't necessarily need to conclusively say that, it might not necessarily perfectly, conclude that there is a design flaw or not. And in particular, once you find this cause of this incident, there's nothing else to learn. So in particular, we're thinking about cases where once you get this signal, once you get this non-signal, that's the thing you've been looking for. And so once you found it, there's nothing else. There's nothing else to learn. Okay, so I think that's kind of I think gives you a sense of the sort of situation this reflects, and we think that's kind of a general that it applies to a lot of different kinds of problems, but it is restrictive. We don't deny that.
Jonathan, a short clarification question. This cost C,
yes,
this is paid if there is a decision to search, or is it always paid, and does it stop when? Is it a sunk cost even if not the signal doesn't arrive?
If you get a null signal, you still pay if you decide if you work or not. If you get a null signal, you decided to work, you still pay the cost. Yeah.
And if you receive that signal, then it's the only signal you will get, and you will never decide to search again and pay.
Exactly.
Excellent, thanks.
Okay, so now I want to talk about the set of contracts that we allow. So at every time, we're going to let the agent send a message from some general message space, as part of the contract. And so what the contract is going to be able to condition on is the history of messages of reports from the agent, which we denote by HT. And so I just want to remind you guys that the designer is going to be facing both moral hazard and adverse selection. So there isn't any other variable from in terms of what the agent is doing that the designer can condition on. What we're allowing the designer to do is choose a reward within the unit interval. And in particular, we're going to assume that this reward is selected deterministically, as well as being, from this bounded set. So I want to say a little bit about that. So, it's not so important that the reward goes to the unit interval and not like randomizations over the unit interval. I'm going to have risk neutrality, in the next bullet point, and so that's not so important. What we are ruling out is, public randomization from the principle. I can talk a little bit about that and how that kind of influences the results. We have some, things to say about that case as well. But our sharpest results are going to be for this case where these rewards are provided deterministically.
Jonathan,
yes.
I have a question about this bounded rewards assumption, right?
Yes.
It looks like even without this assumption, the problem is not trivial at all. Why do you put an additional friction?
It might not be. I think it is trivial given the objective I'm going to have on asking effort maximization. So our interest is in maximizing the amount that the agent exerts effort. And so for that, if we had kind of unbounded rewards, you could implement
Always
any.
Implement. I see.
Yeah.
So basically here you are saying that instead of saying that, okay, each dollar cost me $1, you are just saying that any dollar between 0 to 1 costs me nothing, but any dollar above 1 costs me a lot.
Yeah, you can think of it.
Okay, going back to my first question, now it looks like how informative the end of period signal is going to be very important, right? Because if you learn the state now perfectly, you are not likely to hit the bound as frequently as if you have very uninformative signal about the state towards the end of the day.
We'll talk about this. It is not necessarily even if you had perfectly informative signals, you might not kind of want to give the full reward to the agent. So we'll, that's not necessarily true, but we'll talk about that. But you're absolutely right. It will play, whether the signal is perfectly informative, will play a big role in our main result about whether dynamics helps. But it's I think, at least in my opinion, it's not so obvious. Very good. So now, as I said, the design goal is going to be to learn as much as possible. In particular, given this finding evidence technology, that means that we're going to try to maximize the length of time that the agent works absent signal arrival. Okay. So the goal here is to design one of these contracts in order to maximize the length of time that the agent will work in the absence of a non-null signal, I should say.
One small question.
Yes.
So it looks like, can you give us a hint as to what type of adverse selection problem we are facing here?
Very good.
Agent, yeah.
So the agent is exerting effort. Let's suppose the agent is exerting effort, right? And so they are, seeing, okay, did I find evidence? Did I not find evidence? If you didn't find the evidence, your beliefs might still be evolving, right? So when the agent is exerting effort, that is generating private information about the state. The agent is becoming informed about the state, but it's entirely endogenous, right? Because the agent, has to be incentivized to work. And so, but by incentivizing them to work, we're also giving them private information, which we're then going to have to incentivize them to report back. So that's kind of the sense in which we have moral hazard as well as adverse selection, where that adverse selection is kind of endogenous. Very good.
Jonathan, can you comment a bit on the objective function here? Like the role of bounded rewards that cost nothing up to the bound versus a somewhat more familiar like cost minimization objective?
Yeah, we don't have we have a little bit to say about that in the paper. I'm not sure so I already said that we think about the cases where, given that the goal is to learn as much as possible, where given that the goal is to learn as much as possible, we're sort of treating we would be treating the transfers as zero sum. You could also think about this as reflecting some budget constraints on the side of the principal, together with the idea that information acquisition is kind of lexicographic importance relative to relative to whatever transfers you would pay. So it's really important to learn about the state. You can't give, but it's not, you're still constrained in how much you can give. And so, we really want to focus on that. And another thing is that it could be that this reward itself is non-monetary. So in some cases, we think about, organizational settings where perhaps what you're giving maybe you don't have access to some kind of monetary reward, but you do have access to some kind of gold star, which the agent might care about. So we think there's lots of cases to be lots of reasons you might be interested in. Our characterizations aren't kind of complete for that case, and that's sort of a little bit open for. So I don't know if that answers your question, but
yeah, great, thank you.
Okay. Good.
Hi, another clarificatory question I had about the adverse selection bit. So is my understanding correct that these signals are verifiable, and the adverse selection aspect is that the expert can report a subset of the signals they collect?
No. So I know we use this terminology evidence, and that I understand that can be confusing, but we're interested in cases where the expertise is required to recognize and interpret evidence. So all of it's private. So the designer doesn't see anything other than the messages that are sent from the agent. So that's very important. So the agent, so the signal realizations are not verifiable.
Can I jump in with a related question?
Yeah.
So it seems like if the agent's actions, that is the information acquisition choices, were contractible, then maybe outside of some trivial cases where like the bound on rewards is very small, this would be a trivial problem. You can implement the first best. What about the benchmark where it's pure moral hazard? So you can't contract on the agent's actions, but there is some verifiability of which signal arrived, even if the agent could decide to, say, conceal it for some amount of time before reporting it. Do you know what happens then?
So I believe in that case, you could still give the reward when the signal arrives, and I wouldn't necessarily, need to kind of condition that reward on what the, whether it's evidence for state 1 or state 0. So that would, it would also kind of change things. I mean, that does kind of, it's like you're getting more evidence that the agent was working if you could have this kind of, verifiable signal realization. Okay, very good. This is great. So let me, give some, so this is kind of a pretty general setting. Let me give some kind of simplifications that, perhaps you already assumed we were going to go there, but I just want to be, kind of clear and explicit. So in general, there's a lot of different strategies that the agent might use. They might be randomizing, they might be stopping for some length, they might kind of take a break. We don't have discounting, so there's nothing really that would kind of stop them from doing that. But, it turns out that, kind of some of these strategies, it's to look at all the strategies as maybe unnecessarily, just kind of unnecessarily, just unnecessary. So we'll say that an agent follows a stopping strategy if there's some time, tau, which is the longest length of time that the agent would work absent evidence arrival, okay? So the idea is that the agent will exert effort at any time before tau if they haven't observed this kind of non-null evidence, okay? And if they've only seen null signals, then they're going to stop at time tau, okay? So we have this is one reason the signal evidence assumption is kind of nice, is that it turns out that it's without loss of generality to just focus on cases where the agent is using a stopping strategy, okay? So given some contract R, we can let tau R denote the corresponding stopping strategy that's induced by that contract. And so our new objective is going to be to try to maximize this, this stopping time. Okay, so we're just trying to maximize the length of time that the expert is working in the absence of evidence arrival. Okay, so a little bit of notation. So so we're going to let mu denote the belief of the agent and the evolution of the beliefs of the agent over time. So the subscript, so if the agent sees a signal S at time t, we're going to denote the belief as mu sub t super S. Okay, so the idea is that the agent has only seen null signals before that. They get the signal little s at time t. Okay, and so mu t S is going to be their belief following that case. Okay, if they've only seen null signals, the belief is going to be mu tn. Okay, so we have so the time. So given the restriction to stopping strategies, the time in the signal realization will kind of be a sufficient statistic for the agent's belief. Okay, and you can think about the prior as kind of this, what they kind of before they started working, what was their belief?
Excuse me, just to again clarify my understanding, why is it not without loss or not enough to just screen the agent's belief at the end of capital T?
So our main result will be that that's not necessarily that doesn't necessarily suffice, and I hope to give you some intuition for why that's the case. The short answer is just that if I'm trying to maximize the length of time, if the agent's belief is kind of moving around, then the way to kind of maximize their gain from exerting effort will also in general be changing. So it's not trivial to kind of resolve the tension across different times.
Thank you.
Okay, so first simplification is that we're going to restrict to stopping strategies. The next simplification is going to be that I want to basically think about the reward being offered as a function of the agent's information. Okay, so this is kind of the revelation principle-esque argument that we're going to use. Okay, and so I want to talk through that. So given some history, so what's the agent's going to report, they're going to exert effort, and so on and so forth. At the end of the day, there's going to be a reward which is going to be specified if the state is 0, and then a reward that's going to be specified if the state is 1. And so the idea, so our simplification is going to be that let's make those rewards as a function of the agent's information. So again, we have that stopping strategies are without loss. And so we're going to think about the agent working until some time tau absent signal arrival, right? So at the end of the day, either the agent's only absolved null signals, okay, in which case they've worked until time tau, or they got some non-null signal, but in that case, I only got 1, okay? And so what that means is that, if we want to think about, well, what are these, if we wanted to make the contract as a function of the agent's information, we could let the agent just make 1 signal report because that would suffice to describe their private information, okay? So we're going to use this notation, again, where subscripts denote time and superscripts denote signal realizations, okay? And so the reward that's going to be offered if S is observed at time t is going to be R sub t super S, okay? And so in fact, that's an ordered pair because it reflects 1 reward that the agent gets in state 0 and 1 reward that the agent gets in state 1, okay? And if no signal arrives, we use RTN as the reward. And so if you squint at this, you realize that this is actually closer to the taxation principle rather than the revelation principle, because we're saying that these rewards are kind of given as a that's a sort of a taxation principle argument where that's where kind of the rewards are given as a function of the private information in this way. But let me not kind of talk too much about that.
Jonathan, just to clarify. As the agent, what is the space of my report? Let me clarify. Can I report an arbitrary good signal or bad signal at any point of time?
Yes, very good. So you can. So we're restricting to contracts where we think about the offer as being, the agent is selecting the contract that reflects having received signal S at time t. But the incentive constraints that we're going to be, the relevant incentive constraints are going to be that the reward that you select has to be the one that, corresponds to your type, which is this time/signal arrival. Okay, so the idea is that the reward that you select, RTS, has to maximize your payoff over the set of rewards that are available. So if you get the signal T, if you get the signal S at time T, you absolutely could select the contract, reflecting getting the other signal. You could also kind of allow, you could pretend that you got the signal later than you did, and that would also be completely.
So I can pretend I get a signal that has not arrived yet. So I can report early, I can report later, I can report in arbitrary way. I like
Exactly. But one thing I want to emphasize is that as time unfolds, the set of contracts that you're able to select is going to be shrinking, right? So if I can't, and this is kind of very important and drives a lot of what we get, right? So if you got the signal at time 10 and you really would have liked to select the report you got, the contract you got at time 5, that's not possible, right? So you can report late, you can delay the reports, but you can't kind of go back in time.
Okay.
Okay, so now I want to kind of turn to a little bit of terminology and also just kind of an articulation of our main question again. So a particular kind of contract that the designer might use is just one where you elicit a belief from the agent, and that the report then depends on that stated belief as well as the realized state. So a scoring rule is one such mapping, okay? And so this is kind of a terminology we're borrowing from the literature. And in our context, a scoring rule is a static contract, okay? So we'll say that a contract can be implemented as a scoring rule if we can take the message space to be the set of beliefs, okay? And if given any history where the last message is empty, it's enough just to specify the reward as a function of that last message as well as the state. Okay, So that's this is what we mean by a static contract. And in particular, the main question is going to be whether the effort maximizing contract can be implemented as a scoring rule. Okay, and in particular, coming back to this earlier question, because the beliefs of the agent might be changing over time, it could be that allowing for multiple reports could provide better incentives for dynamic information acquisition. And what I'm going to talk about now is kind of suggesting why actually that should be the case. And so what our main results are going to provide first sufficient conditions such that the effort maximizing contract can be implemented as a scoring rule, as well as cases where dynamic contracts can actually be strictly beneficial compared to scoring rules.
A quick question here. This might just be technical without any real substance. But there are lots of scoring rules, like the log scoring rule being maybe the most famous one, that have unbounded rewards, and in particular, punish the agent with negative infinity payments if they guess the wrong state with the degenerate posterior report. How is your bounded rewards restriction limiting the space of scoring rules in any substantive way, or like can we always adjust things by adding constants or something like that?
So I mean, I took out my literature slide where I'll put it because I was a little worried on time, but I mean it does kind of it does matter. I think if the question is like, how do I implement getting the agent to work 1,000,000 periods, right? Then you can kind of use very large, give you a very large reward if you kind of guess the correct state. I think what you're right about is that to some extent, if you had a very negative reward, you could just kind of like scale. You could do this kind of scaling. So there's a sense in which the restriction to 0, 1 is, once you've kind of restricted some bound, the restriction to 0, 1 is kind of, without loss. But the presence of the bound is kind of necessary to avoid the case where you can exert infinite effort. Yeah. Okay. Any other questions before we get into some analysis? Okay. So what I want to think about to understand, why is it the case that there's this kind of tension in the model, I want to take a small detour to talk about, the natural, in my opinion, really the natural static model that is embedded within, or rather the natural sequence of static models embedded with our dynamic model. And the idea is that these static models are going to be ones where I only think about the incentives to exert effort at some time and then report at some later time. Okay, so that basically takes this dynamic model and then drops all incentive constraints that kind of make it dynamic. So more specifically, we're going to think about a static game where the agent is just making one binary effort choice, where the decision is whether you want to work between time t and time t prime. Okay, if you don't work, no effort arrives. Okay, and then at time t prime, you need to make a report about the belief. Okay, and so given that we have basically two actions, this is now a static game, and we call these static games the continuation game between time t and t prime. And so the very natural question to ask is whether we can implement effort in this continuation game. That's kind of a first preliminary question. How can we do it? And if we can do it, how would we do it? Okay, and it turns out that question is one that we kind of know from the literature. And in order to answer it, I want to introduce this notion of a V-shaped scoring. So you can think about a V-shaped scoring rule as a guess the state scoring rule, okay, where the idea is that if the agent's belief is above some threshold, okay, then they guess the state as 1. And then if they're correct, they get the payoff of Z1. Okay, and if their belief is below some threshold, then they guess the state 0. In which case, if they're correct, they get the reward Z0. Okay, and if they're wrong, they get nothing. Okay, so in terms of what this looks like, we can represent this scoring rule as a kind of step function where they get the guess the 0 reward. the guess to zero reward is state Z0, and then the blue line is what they get when they guess state 1. Okay, and so if the terminology is V-shaped scoring rule, and you might, if you're astute, you might realize this doesn't look like a V, so why is it called a V-shaped scoring rule? Well, the reason is because if you look at the indirect utility function, that looks like a V. Okay, so we call this intersect, so you have one kind of reward function when you guess state 0, one reward function when you guess state 1, and in terms of indirect utility, those are kind of those are both straight lines, okay, with non-zero slope. So we refer to this intersection point as the kink of the V-shaped scoring rule, and the kink turns out to play a very important role for understanding whether it's possible to implement effort or not in these continuation games. Okay, and so this result actually is due to Yingkai from an earlier paper, which is that if it's possible to implement effort in some continuation game, then it's also possible to implement effort using a V-shaped scoring rule. So in particular, a V-shaped scoring rule where the kink is at the prior belief. Okay, so I want to put this kink at the belief of the agent, and the idea is that that's going to minimize, or sorry, that's going to maximize the gap between what the agent gets in the absence of exerting effort, which is their payoff at the kink, versus what they get if they do exert effort, which is some convex combination of points above the kink. Okay. In the interest of time, I do have some more intuition for this, but in the interest of time, let me maybe skip over that and we can kind of come back to it later. But the point is just that, and what you can kind of see is that it's very important in order to implement effort to have, if I want to be sure that I can implement effort, to locate this at the kink, okay? And so the issue is that as the beliefs change over time, there's going to be tension between these different V-shaped scoring rules because the belief is going to be moving. So I want to illustrate that a little bit right here. So what I've drawn in this graph is first the payoffs that the agent gets when not exerting effort, when just kind of deciding to make a report. And in that case, they'll decide, do I want to guess state 0? Do I want to guess state 1? Okay, and as a function of their belief, that'll put them on the kind of upper envelope of these two red lines. Okay, and so this point. So if the agent doesn't exert effort and they just kind of make this optimal guess, then their payoff will just be something on this red line. Okay, now if they do decide to exert effort, okay, then they're going to be working until either they never get this non-null signal, or they get it eventually. Okay, and so that's going to be the result of some dynamic process, and so that's going to be possibly above these red lines. And what I want to emphasize here is that if the agent's belief is very, very close to 1, then in that case, they're going to have to exert effort. They're going to have to be exerting effort in order for their beliefs to move. And so maybe if they're already certain enough that the state is 1, they'll just kind of guess 1 initially off the bat. Similarly, if they're kind of very close to thinking that state 0 is the true state, and they have to pay these costs in order to learn anything, they might just kind of go with their default and guess state 0. And so we have this term. So if you look at this graph, you'll see that the payoff from exerting effort, it is only kind of strictly above the no effort payoff in a particular intermediate range. Okay, so we let mu lower bar be the lowest belief such that the agent is still willing to exert effort. Okay, and we let mu upper bar be the highest such belief. Okay, and in particular, these are both going to be bounded away from 0 and 1. So you're not going to be able to get, given these bounds on the rewards, you're not going to be able to get the agent to work if their belief is just below 1, and you're not going to get be able to get the agent to work when the beliefs are just above 0. Now, in particular, remember our normalization is that in the absence of evidence arrival, the beliefs are moving towards state 0. Okay, so they're kind of moving to the left. As the agent is exerting effort. And what that means is that if I'm setting mu lower bar, if I somehow manage to make mu lower bar be lower, then that's going to get the agent to exert effort for longer. And similarly, if mu upper bar is higher, then that means that I can get the agent to start working even when they're more sure that the state is theta equals 1. And our observation is that both of these are decreasing in Z1. So this relates to the point as to why don't you just always give the full reward in both states? Well, the issue is that if you make this reward very, very large, then what you're doing is you're decreasing the largest belief at which the agent would be willing to start working. So if the agent is initially so you could easily be in a situation where the agent is initially pretty certain that, but not completely certain that the state is 1. And if I give them the full reward, then that just leads them to go to their prior belief. Okay, or that just kind of leads them to default with their prior. But if I were to lower the reward a little bit, then I could incentivize them to start start working. Okay, and so one thing you can see here is that you could be in a situation where there are static scoring rules, V-shaped scoring rules, which can get the agent to work from between belief mu0 and mu1. And also a different scoring rule that gets the agent to work between mu1 and mu2, but I can't get the agent to work from mu0 to mu2. Okay, and that's entirely kind of due to this lemma, right? Because you could be, in a situation where, I have, in order to get the agent to start working, I have to have one Z1. In order to get the agent to continue working, I have to have another value for Z1. Okay, and these are kind of inconsistent. That if I had the value for Z1 necessary to get the agent to work to mu2, then I wouldn't be able to get them to start working at this higher belief. Okay, and so this is kind of this main challenge we face, that if we want to maximize the gain from exerting effort, that this objective might be inconsistent over time. So this is underlying a lot of our intuition and the results. And so in the last 15 minutes, I want to kind of talk about these kind of precise results. So we do have a characterization of how to induce maximal, what kind of dynamic contract induces maximal effort, and indeed it can be implemented using a sequence of scoring rules. That characterization doesn't yield the main results that we're talking about, but just to kind of be clear that having this sequence of rewards that change over time in this way can in fact implement maximal effort in general. The other observation is that if it's possible to use a V-shaped scoring rules, and which is a big if, okay, but if it is, then this intuition tells you exactly which scoring rule you should use. What you should do is you should try to minimize mu lower bar of Z1, subject to the initial belief being kind of within this range where you start working. Okay, so so in particular, you'd like to use kind of a lower value of Z1 to get the agent to work longer. Okay, but your value shouldn't be so low that other way around. You want a higher value of Z1 so that the agent works longer, right? But it shouldn't be so high that your belief is kind of outside of this interval, that your initial belief is outside of the interval at which you start working. Okay. And the other observation is that it might also kind of be necessary that this dynamic effort maximizing V-shaped scoring rule doesn't necessarily put a kink at the prior. Okay, so whereas in the static case that is kind of the thing that determines where it's located. So I want to tell you what the main results are. So we have this finding evidence technology, and the way it generalizes perfect Poisson learning is that we allow for signals to be inconclusive. So it doesn't necessarily reveal this. So finding the evidence doesn't necessarily reveal the state. And also bidirectional in the sense that you could find evidence that exonerates the state or incriminates the state. It could be that the evidence suggests a design flaw. It could be that it suggests pilot error. Our main result is that if one of these holds, only one, then a static contract will suffice. Okay, and most one of these. So if the evidence is inconclusive, but it's unidirectional, or it's bidirectional but perfectly revealing, in both of those cases, a static contract will suffice. However, if you both have inconclusive signals and bidirectional signals, then for some range of parameters, it's going to be possible for dynamic contracts to outperform static contracts. Okay. So the punchline is that kind of both of these relaxations of Poisson are necessary in order to have dynamic contracts outperform static ones. Okay, and that if we only have one or the other, then we'll still get static contracts being optimal. And so that's what I want to talk about for the rest of the time. So
so Jonathan, can you help us with what's the condition for inconclusive? I'm looking at the lambda 0G, lambda 0B, lambda 1G, and lambda 1B. So what's the definition of inconclusive?
So I have
Oh, you have them on your slides.
yeah. So I have
And
I have to be conclusive. So it's conclusive if you only get the good signal in state 1, and you only get the, if you see the good signal, you know the state is 1. If you get the bad signal, you know the state is 0. So it's inconclusive if upon getting evidence, you don't necessarily know the state.
So it's inconclusive if at least one of lambda 0G or lambda 1B is strictly positive.
Yeah, in our characterization, I believe we need both. To
You
be
need
strictly
both.
We need both for in our kind of examples.
Okay. So you cannot be like partial inconclusive.
Yeah.
Okay. And how about the bidirectional?
Examples where we get if we only have, if you only have good signals, then we'll have static as even if it's inconclusive.
Okay. So how about bidirectional? What's the definition of bidirectional?
Bidirectional means that good signals happen and bad signals happen.
So both signals can happen. Okay.
Both signals can happen. That's right. If you can only have good signals, then it's unidirectional.
Okay.
So in other words, as long as the signals are not perfectly revealing, static contract suffice. Is that a correct takeaway?
So if the signals are not perfectly revealing and bidirectional, then it's possible for dynamic to outperform. If you have inconclusive signals, but only if the signals are inconclusive, but they're only good news, then static suffices. If you have perfect, and if the signals perfectly reveal the state, but even if it can go good or bad, then it also suffices.
Thanks.
So if at most one of these holds, static suffices. It fails when kind of both of these are sufficiently strong.
Do you have some good intuition for this result before we move on to
well,
the
so
details?
let's I mean, I'm going to talk about the proofs now. So maybe we can kind of, if that, we can maybe talk about that afterwards. So the kind of the easy case, so there's one kind of asterisk to what I just said, which is that, if you have, you need, in order to have something kind of non-trivial, you need beliefs to move in the absence of evidence arrival. And so if, you were in the setting where if your beliefs don't move, in that case, it's kind of, I wouldn't say trivial, but not so difficult to say that, well, we just said that in these continuation games, the effort maximizing scoring rule is one where the kink is located at the prior. And so if the prior is not changing over time, there's no inconsistency. And so you should just use a V-shaped scoring rule with a kink at the prior. So the second case, where the kind of the less trivial case, and this is the proof I wanted to talk through a little bit, is one where what we call the perfect learning environment. And this is where the state is fully revealed once you get this non-null signal. So once you get the non-null signal, you know the state. If that's the case, then we're in what we call the perfect learning environment. And our result is that in the perfect learning environment, there's an effort maximizing contract that can be implemented as a V-shaped scoring rule. Okay, so a V-shaped scoring rule can implement the effort maximizing contract. Now, this contract is always going to involve the full reward in state 0 and some other reward in state 1. Okay, and so in particular, this other reward, it doesn't necessarily need, to be 1. But one kind of observation we make here is that, well, if you think about what is the kink in such a contract, it's 1 over Z1 plus plus 1, right? And that's always greater than a half. So the key point is that for this kind of information arrival technology, the V-shaped scoring rule that is effort maximizing has a kink that's above 1/2, okay? Which is true even if the initial prior is below 1/2. Okay, so so very good. So I want to talk through this proof. It's kind of fun, and hopefully that will give kind of some intuition as to why why static can suffice despite this, inconsistency in terms of inducing maximal effort over time, which is present in this setting because the belief is changing in the absence of evidence. So our initial kind of restriction on the contracts invokes this menu representation, and so we can restrict to cases where the agent gets some reward after signal S at time t in state theta, and then if they never see any informative signal, they get this reward RTN. Okay, so this is kind of the restriction that we get using our menu representation. So there's a couple of the first easy simplification is that since we have perfect learning, there's never a reason to give any reward if the agent says they got the signal and they guess wrong. Right? If the agent says I got the good signal, then in this perfect learning environment, they should know that the state is 1, in which case if the state isn't, if they're in fact wrong, that's kind of just that shouldn't happen if they were actually telling you the truth. Right? So there's no reason to give this positive reward given perfect learning, because if they were to kind of guess the state, they should be correct. Right? So that's the first kind of simplification. The second is that because the agent always has the ability, if they kind of get some positive reward, if they get some signal, they always have the ability to delay their report. That means that you would never want to use a reward which kind of increases over time, that strictly increases, because in that case, that's just kind of allowing the agent to shirk and lie, right? They can just say, oh, I got, or rather, sorry, it always just encourages the agent to delay their report, right? Because then if the reward is increasing over time, then they would want to do that. Okay, so these incentive constraints imply that the rewards that we're getting should at the very least be weakly decreasing. Okay, so we can already restrict to those kinds of things, which just follows from the fact that the agent can always delay the report. Okay, so the first step to this proof is to say that I want to maximize the rewards that I get in state 0. So I want to give the agent everything I can if the state is in fact 0, which means that if they get the bad signal or they get no signal, or they never get a null signal, I want to kind of make sure that they're getting the full reward in that instance. Okay, so why is that the case? So to talk through this, and I think it's intuitive once you kind of see this. And so for me, the way I like establishing the intuition is to think through the case where the agent is just about to stop working. Okay, so I want to think about the case where the agent is going to, guess if they can either decide to not work, or they can work for one more period, in which case then they'll stop working. And I want to think about what is the constraint that says that the agent wants to continue working. Well, if the agent works one period and then guesses state 0, so then they've kind of, their belief has gone to state 0. So what do they get in that case? Well, they have to pay the cost from exerting effort. Now, there's a chance they get this good signal, and that happens with probability mu t n lambda 1g delta, right? So with some probability, they get the good signal, in which case they then get this reward, the reward for state 1. Okay, there's also a chance that they don't. Okay, in that case, they either get the bad signal, which means they guess state 0. In that case, they get RT0B, right? If they get the bad signal, or they wait one more period, in which case they get RT0N, because the assumption is that they are going to stop working in the next period, right? They could also just stop immediately and guess state 0. In that case, they would get just the probability that the state is 0 and then RT0B, right? Very good. So so the first observation is that, well, our goal is to kind of increase the first line and not kind of increase the second line. That's kind of how we maximize the gain from exerting effort. Okay, and so the idea is that the first thing we can do is just change this RT0N to RT0B, because these are decreasing over time. And so if we kind of increase the reward that the agent gets when they get no signal ever, then that's going to, as long as we don't increase it by above RT0B, right? That's just going to make the exerting effort kind of more attractive. Okay, so first what we do is we increase RT0N to be exactly equal to this kind of next to last next to last reward from guessing the bad state. And now when we do that, we see that if I can adjust RT0B, because here the comparison of whether it's exerting effort versus not is going to be constant in RT0B, right? If I increase RT0B, I'm kind of I'm increasing the payoff you get from stopping immediately, but given that I've set RT0N to be RT0B, I'm kind of also increasing the payoff from exerting effort by the same amount, okay? And so once I've kind of made this adjustment, it actually doesn't matter, what RT0B is. If you're kind of willing to work for some level of RT0B, you'll still be willing to work at some different level. And it turns out the other cases are kind of also just basically boil down to the same intuition. So if I'm kind of making this change where I increase all rewards from guessing in state 0 to be 1, in that case, the increase in continuation is always going to be at least 1 minus mu Tn times 1 minus RT0B, right? That's always going to be at least what you're getting. Possibly even more in the case where, RT0N is kind of also increasing by some amount. On the other hand, the increase in payoff cannot be larger than 1 minus mu Tn times 1 minus RT0B, right? That's what it would be if you were going to guess state 0. Perhaps you're actually not guessing state 0, in which case actually your increase in continuation isn't changing at all. So it's possible it actually doesn't change. If it does change, it can't change by more than this amount. And so what that means is that the increase in continuation is always at least as large as the gain from stopping. Okay, and so what this kind of argument shows is that it's without loss of generality to give the full reward when guessing state 0, and that happens if you're either only observing the end signal or you eventually get this bad signal. Okay, and so what this leaves open is the possibility that RT0B is changing over time, and so now we have to rule that one out. So now what we have to do is we have to show that the rewards that you get in state 0, I can replace that with one single reward. So what I've drawn here is the agent's payoff if they were to so these good rewards that they're getting, again, these are also decreasing over time, right? So as the agent exerts, as kind of time unfolds, if the agent were to guess state 1, we know that because they can always delay, we know that the rewards that they're getting can never be increasing strictly, right? So what I have here is this black curve, this thick black curve, is what the agent would get if they were to guess the state 1, given their belief mu Tn, right? So these are the rewards that they are kind of passing up by continuing to exert effort when they to get the good state. Okay, and so the red line is what they get when guessing state 0, right? Which we've kind of already said, it suffices just to look at one reward in that case, right? Where you get the full reward in state 0. Okay, so we have this black line, and you'll notice that, so because these rewards are decreasing, the black line has to also be decreasing as well. Okay, and so at some point, this black line will intersect this red line, okay? And if at this intersection point, that intersection point is going to correspond to some, convex combination between getting 0 if you're wrong and getting something if you guess state 1 and you're right. And the idea is that we let that time at which this black line intersects this red line, and we define that to be, that time to be t hat. Okay, so we identify this one time, reflecting, the agent being indifferent between guessing state 0 and guessing state 1 if they were to guess, okay? And the idea is that we replace all of these possibly changing rewards over time in this good state and from guessing state 1, and we replace it with the single reward RT hat G, okay? Now, what is that doing? So remember, these rewards are decreasing from guessing the good state are kind of weakly decreasing over time. And so that means that the agent is getting more when they get state 0, when they guess state 1 after t hat, but they're getting less before t hat. Okay, so this kind of replacement is because these rewards are decreasing over time. If I replace everything with the reward that they get at time t hat, then that's going to be giving them more from guessing state 1 if they were to do so after t hat, but less before. Okay? And it turns out that this kind of replacement always will lead to stronger incentives to exert effort. So if you're at some time after t hat, then when I make this replacement, well, if I were to stop working, I wasn't going to be guessing state 1 anyways. I was going to be guessing state 0, right? Because the red line is above the black line. So if you're at some time t above t hat, then by what we're doing is we're increasing the rewards, and that's leaving the utility that you get from stopping unchanged, but it's weakly increasing what you're getting if you guess state 1. Okay, so that's going to lead to stronger incentives to exert effort. At these higher times, the utility from stopping isn't going to be changing, but you're going to be doing strictly better if you decide to exert effort, because there's a possibility your beliefs jump to 1. And so now in that case, you're actually getting a higher reward in that event. On the other hand, if your belief is below t hat, in that case, if you were to stop, you were going to get something on the black line. So in that case, the black line is your stopping payoff, right? If at times before t hat. And in that case, the reason why it's better to decrease the reward is because there's some chance if I exert effort that I actually do learn that the state is 0, in which case you get this higher reward, right? So your payoff from stopping is kind of decreasing, and it's decreasing in a way proportional to your belief, right? Because if you guess state 1, because if you were going to stop, you were going to guess state 1. Okay, but your continuation payoff is going to be decreasing not by as much, because you're still getting this full reward if in fact you learn the state is 0. Okay, so the idea is that by changing this, by kind of lowering the reward you get before t hat and increasing the reward you get after t hat, that kind of always leads to stronger incentives to exert effort, thinking about these case by case. Okay, so I think I'm a little bit over time, so I should maybe wrap up. So we also have the same observation in the case of the single signal environment, if there's only one non-null signal. In this case, our result is that there's an effort maximizing contract that can be implemented as a scoring rule. It doesn't necessarily need to be V-shaped, okay? So it's possible that, so we know that, if learning were perfect, then the previous result we just would say that it should be V-shaped, but it's possible you'd want to provide some strictly positive rewards in both states, even in that case. And so this kind of has some interpretation of giving the agent a positive reward just to kind of maximize the dynamic incentives. Okay, so as I said, we do have kind of to kind of show that all of this work, you might have thought, oh, could we always show that static is optimal, to kind of emphasize that there is something, kind of that it's not just a degeneracy, it's just not just a degenerate case. So what we do is we identify a set of parameters such that the effort maximizing contract cannot be implemented as a static scoring rule. And roughly speaking, these conditions boil down to a violation of each of these individual conditions. So we needed to be, first, we kind of need to avoid degeneracy. So we need to have kind of sufficient incentives to work in the first place. Okay. Then we also need there to be kind of, so our first condition was that signals are perfect. And so our first condition to have something where dynamic is better is that the signals are kind of noisy. They're sufficiently noisy. And the second condition is that the beliefs drift quite slowly, in the sense that the arrival rate between signals in state 1 versus state 0 are not kind of too far apart from each other. And there's some sense in which that assumption is kind of the extreme opposite of the assumption for the single signal case. Because this kind of the arrival of evidence in state 0 is basically just slowing down the drift. And this, I need to have kind of enough arrivals in state 0 in order to get this result. So I'm out of time. So there is a relevant literature but we can leave that for a discussion. I'm happy to talk about any of these papers if people are interested. And just to kind of remind you of what we did today, we had this question of when is it the case that implementing kind of maximum effort from the agent required varying the rewards that you would be provided over time, and in particular, having multiple elicitations. So we identified 3 cases where the effort maximizing contract could be implemented as a scoring rule. These cases are first reflecting the beliefs not moving in the absence of evidence arrival. The second case is where the signals perfectly reveal the state. And the third case is when there's only one kind of non-null signal, where you only have good news. Even in these cases, we kind of talked about how the dynamics kind of influence the design of the scoring rule. So in particular, I think the sharpest kind of point here is the possibility of a strictly positive minimum wage. And what we also showed is that it's not necessarily you shouldn't take it for granted that static suffices, because if we have violations of these conditions, then it's possible to have no effort maximizing contract implemented as a scoring rule. So in kind of given violations of these conditions, we actually need to use dynamic contracts if we want to maximize the information acquired by the agent.
Okay, so thank you, Jonathan. We're kind of running out of time, so I suggest that maybe we can have time for short questions from Yingni and Alex. So Yingni, if you want to start.
Yes. Jonathan, can we go back one slide?
Yes.
I'm thinking about the third environment. You are thinking about the single signal environment. So this is the case that in both states, we can have good signals, but if the state is one, good signals arrive more frequently.
Exactly.
Right? So this is like inconclusive good news case. So typically it's a mass, right? So when we think about using this model for other settings, but I just want to confirm here, it's simpler in your setting because you only allow for one signal. Is that true?
Exactly. 100%. Yes.
Okay.
If we
so
have, so that's one of the main difficulties with generalizing, as you exactly what you alluded to, that it becomes kind of a giant mess when your beliefs kind of move to something, and now you have to solve for the value function at that point, and it's not
Okay. So just one small question. I think you talk about these 3 cases. It's more like comment. It would be very nice to tell the audience what is common among these 3. What is driving this result that a single scoring rule is actually sufficient for the environment, right? So we don't have to think case by case. But I should give the stage to Alex. Yeah.
Great. So thank you. I guess most importantly, let me start by saying I really like this paper. You're studying a very fundamental class of problems, and the idea that information acquisition is inherently dynamic is one that I certainly sympathize with, and I think is very realistic. And these are also very hard problems, and you guys have written down a model that is surprisingly rich and also surprisingly tractable. So I think these are all real positives. I think my main questions are sort of big picture ones in line with Yingni's second question. So first. It would be nice to know how you guys view sort of the general sort of top line takeaway from this result, in the sense of, do you view this as a positive result, showing that there's a natural class of environments in which static and therefore, in some sense, simple contracts are optimal? Do you view this as a negative result, kind of an impossibility result about the optimality of static contracts in realistic settings? Or do you want to sort of be agnostic, and this is really just meant to be a classification of the kinds of different strategic forces that are involved in the 2 cases? And particularly if it's the third sort of more agnostic interpretation, it would be really nice to have some kind of identification of general principles that are driving things across the three cases. Or even if even if the strategic principles are different across the three cases, to have a sort of more intuitive understanding of those. Yeah, I'm happy to take more conversation offline.
Yeah, no, that's very fair. I mean, it's something I think we have to have to meditate on, and I'm sure we'll have, I'm sure if you ask me on different days, I would give you a different answer. I don't want to speak for Yingkai. He may have opinions on this as well. I tend to be a little more agnostic, personally. I think, we write down the model which like you said, we thought it was kind of a natural model where perhaps we could get something interesting, and so and we just wanted to kind of see what would happen. But yeah, in terms of kind of general principles, I think, yeah, there's always room for more. And I think we would love to have kind of more to say, and we'll certainly, I think about that.
Okay, so excellent. So I think it's kind of perfect timing to finish the official part of the seminar, and I would like to thank Jonathan, for this very nice talk, and also want to thank the participation of Yingni, Alex, and Yingkai. So, and thank you the whole audience for coming one more week. So I'm going to stop the recording.